All right, so in addition to determining relative acidity and basicity of molecules using pKa's, there's another thing that we can do with pKa's that are pretty cool. Now let's say that we're just given this. We're given that there's going to be a mixture of water and ammonia, and we need to figure out what the products of this reaction are. Well, both of these have protons that can potentially be donated, as well as lone pairs, which can potentially accept electrons as bases. So one of the first things I have to figure out in my acid-base equation, balanced chemical equation, is who's playing the role of the acid. So this is another instance where pKa's can be really valuable. So take a look at your pKa table and look it up for each of these compounds here. For ammonia, it's got a pKa of 36, whereas water has a pKa of 15.7. I should double check that. Okay, so that means that water is the stronger acid out of these two because it has the lower pKa, right? Lower pKa, stronger acid. So that means that in this balanced chemical equation, or in this reaction right here, water will be playing the role of the acid. I can tell who's going to play the role of the acid depending on who has the lower pKa. So this is my acid, this is my base. Once I've identified my acid and base, I can go in and draw the structures for my products, my conjugate acid and conjugate base. So everybody pause and do that example real quick, and then you can play it back and see what I've got. So if water is an acid, that means it's going to be donating one of these protons. So the conjugate base would be OH minus. And then the conjugate acid is what happens when my base accepts a proton. So now it's got an additional proton on there, so it's NH4. And in doing so and accepting a proton, it also has a +1 to its formal charge. Okay, so this is my conjugate acid. Okay, so now the next question that we can answer with our pKa. So first of all, first thing we got in terms of our balanced chemical equations is who's playing the role of the acid, who's playing the role of the base. We can use pKa to determine that. The next thing that we can answer is which direction does this reaction favor? Does it favor the formation of products, or does it actually favor the reactants, meaning there isn't very many products formed? And in order to do this, we have to sort of consider the fact that acid-base reactions will favor the formation of the weaker acid. So what do I mean by that? Well, if you notice in all of our acid-base reactions, we have an acid on our reactant side, but we also have an acid on our product side, the conjugate acid. This reaction will go in the direction of the weaker acid. So in order to tell which way this equilibrium lies, does it favor products, does it favor reactants, you got to look up the pKa of your conjugate acid. So if you go to your pKa table that I gave you, you'll be able to find the ammonium ion, NH4+ on there. And that has a pKa of 9.4. Okay, so again, I'm going to compare my two acids on my reactant side and my product side. This reaction will favor the formation of the weaker acid. So which one's the weaker acid? Remember, weaker acid means high pKa, strong acid means low pKa. So water is actually a weaker acid than the ammonium ion. So this reaction will actually favor the reactants. So what exactly does that mean? Well, when we mix water and ammonium, yes, there might be some product that's formed, but the vast majority of those molecules remain reactants. They remain ammonia and water. Only a small amount of ammonium and hydroxide are formed. So let's take a look at another example here. Again, we have our acid and base designated, so then I can form my conjugate acid and conjugate base. And then I'm going to go and look up the pKa of my acid. So again, in this case, it's water at 15.7, as well as the acid on the product side, which is my conjugate acid. In this case, that's that tert-butanol again. This has a pKa of 18, whereas water has a pKa of, around 16. So again, formation of the weaker acid. Which one of these is the weaker acid? That's going to be the one with the higher pKa. In this case, my reaction is going to favor the products. And so notice how that's sort of drawn in terms of these arrows here. You have a big arrow pointing at the product side and a little arrow pointing back at the reactant side. That's one way that you can sort of diagram out that this reaction favors the products. One more thing to note is the larger the difference between the pKa's, the more it will favor one direction or another. So let's take a look at another example here. Here my base is actually a carbanion, and my acid is again water, so we got that down. pKa of water is the 15.7. Well, if I form my conjugate acid, that's just this butane here, right? Because there are 1, 2, 3, 4 carbons. And the conjugate acid of the pKa of the conjugate acid is around 50, extremely, extremely high. Basically, that means that this is a terrible acid. It really doesn't want to get rid of that proton. You need something crazy strong to come and pull that proton off. And so this reaction strongly, strongly, strongly favors the products because of that huge difference in pKa between your reactants and your products. Okay? Again, favoring the weaker acid. So in this case, you may see this arrow drawn as just a single direction, meaning that there's really not much of your reactant left over once you mix these two. Very, very, very minuscule, tiny amounts, 0.00001%, something like that. So the larger the difference in the pKa, the more it favors one particular side or the other. Okay, and again, always towards the weaker acid or the larger pKa.